All right. Now that we have done the general stories about isomers and how to name organic compounds and so on, maybe we can start more systematically to discuss the most important homologous series that we're going to need, like the alkanes and the alkenes and the alcohols and something more. Now, let us start from the alkanes and alkenes, which are hydrocarbons. And lots of these we have seen before, lots of the aspects we're going to discuss we have seen before. It's fine, it will be like an overview, and we'll add some more detail. So alkanes and alkenes, remember, they are both belong to the hydrocarbons, and hydrocarbons, the word hydrocarbon means that these compounds consist of only hydrogen and carbon and nothing else, only hydrogen and carbon, both of them. So we have, of course, an important atom of these compounds is the carbon, and carbon has 4 valence electrons, and therefore it can form 4 bonds, and that is why we say that they have a valency of 4 carbon atoms, and these hydrocarbons come into types: the alkanes and the alkenes. The alkanes are in the alkanes, all the bonds that this carbon can form are single bonds. So each carbon bonds with 4 different other items, and all the bonds are single, and not just single, but covalent. So the alkanes are characterized of single bonds between the carbons and between carbon and hydrogen. There are 2 types of bonds that we can find in the alkanes, either between carbon-carbon, bonds between carbon-carbon, or between carbon and hydrogens. But whatever bonds we're going to see, they're all single and covalent. Now, for the alkanes in particular, all the alkanes have this molecular formula, this general formula, where N is the number of carbons in the chain, and the hydrogens then will be 2N plus 2. And here I have some examples of alkanes. Look at this with the simplest alkane is the methane with 1 carbon, and you can see all the bonds of the carbon. All the 4 bonds that the carbon can form is with hydrogens. So this is a molecule of methane, the simplest alkane. This is the next simple alkane, which is made out of 2 carbons, which we call ethane. And you see there is only 1 bond between between 2 carbons, single bond, and all the other bonds that can form are with hydrogens. And if you count the number of hydrogens and compare them with the number of carbons, we are going to see that they follow this general formula. For example, here we have 2 carbons, so we have carbon 2. The hydrogens will be 2 times 2 plus 2, 2 times 2 plus 2, so it's 3 plus 3, 6 altogether. You see, 2 times 2 plus 2, this makes 6. 2 times 2, 4, plus 2, 6. All of them are of the same general formula. Here we have one with 3 carbons, which is the propane, and here we have the butane. If you check again the butane, if you check the number of carbons and the number of hydrogens in each and every one of them, you are going to see that they follow the same general formula. We're going to talk again about these hydrocarbons here, these alkanes, because these are important fuels of ours, but we're going to talk about this again. And in generally, if you remember, here we have the first 10 of the alkanes, the 10th being a molecule with 10 carbons and 22 hydrogens. just to compare how the molecules can look like. So here we have the molecular formulas. Remember the three important types to represent a molecule of an alkane, of any organic compound. Actually, this would be the molecular formula that gives generally how many atoms of each type are there in the formula. So this is what is this, molecular. So this is the molecular formula of these alkanes, from 1 up to 10. This is the structural formula that shows, which is a bit more detailed formula to represent a molecule of an alkane, where we can see it's like separating each carbon and showing with how many hydrogens each carbon is related, is linked. And by the way, because as we go down the chain, as the chain grows with more carbons added, with its own hydrogens, of course, you see it becomes too long now to write. And therefore, we can also write it like the decane, for example, that has 10 carbons and 22 hydrogens. Instead of writing all this long chain with 10 carbons and the hydrogens, we can write all these repeated units here, these are the repeated units, if you notice, in each of these molecules. Because there are so many of them, we have here 1, 2, 3, 4, 5, 6, 7, 8. 8 of these groups that repeat in the decane. So as you can see, we can write the formula with the first carbon and the last carbon and the hydrogens, and in between groups that are repeated, we put them in parentheses and we place an 8 outside the parentheses so that we can write it in a shorter form. So for example, okay, this is for the decane. The nonane, how could we write the nonane? We could write it 3, there's supposed to be 3. Terrible writing, eh? This repeated unit inside the parentheses, here it would repeat like 7 times, isn't it? And the last group with 3 hydrogens. The first and the last have 3 hydrogens because they are at the 2 ends, of course. So there is another way, in other words, to write this structural formula of our molecules, of our hydrocarbon. In this particular case, these are alkanes. All right, and also this column shows how many, we don't need to know that by heart, of course, but just to compare, since we have it here, it's nice to talk about it, how many isomers each of these molecules can have. And remember, these molecules here represent like chains of carbons, not rings, chains, with carbons one after the other. If this is one long chain of 10 carbons, for example, this molecule could have 75 possible isomers because it can branch so much that we can have so many isomers. Whereas the butane with only 4 carbons can only have 2 isomers. And the first 3 smallest molecules don't have any isomers because you cannot branch or do anything to this chain. But as we go down, as the number of carbons increase in the chain, you can see how the number of isomers also increase. In fact, here there are so many that it's kind of mind-boggling. Here, how many carbons do we have here? It's a pentane. You see this pentane, this one. And these are the isomers it can form. You see, there are only 3. It's just the way the chain can be branched. And we can see these 3 isomers, indeed 3 isomers. We cannot find any other isomers of pentane, these 3. And indeed, according to this table, we can have 3 isomers for pentane, and so on. All right, now let us discuss some other important aspects of the alkanes. Like there's a trend in the boiling and melting and boiling points, not just boiling. Okay, I have here boiling points, but also in melting same trend applies to their melting points of the alkanes. And what is the trend? That as the number of carbons increases in the chain, so does the melting point or boiling point. So the more the carbons in the chain, the higher the melting and the boiling points. And here these two graphs kind of represent this trend. You see, this is for one carbon, like this would be for methane, for example. This is for 2 carbons, for 3, 4, and so on. Here, the number of the carbons are shown here. So as the number of carbons increase in the chain, the melting point and the boiling points also increase. I mean, the temperature where these substances melt or boil increases. And it makes sense because if you remember, we spoke about that last week. Remember, as the chain grows, let's see a long chain. Like let's look at this long chain. Straight, we're talking about straight chains, okay? Like this pentane. If you have lots of molecules of pentane nearby, like in a proper sample where we have lots of molecules, billions of molecules together, you see, because they are long and the molecules interact, the longer the molecules, the more they will interact, like sideways. Like you see this part of the chain. If another chain with carbons here is next to this chain, next to this molecule, they will interact with weak intermolecular forces, and makes it harder to separate them. We need more energy, the input of more energy to separate different molecules and make the substance boil, usually, or melt if we are talking about low temperatures. So that is why the melting and boiling points increase the longer the chains of carbons are. And here are the values of the melting and boiling points, just to see them in the form of a table. Another interesting thing to see here, since we have this table, is that the small molecules, the methane, ethane, propane, and butane, actually up to butane, up to butane here, you see that these are gases. The small molecules are in a gaseous phase, in a gaseous state, at room temperature, that is. They are at room temperature in the form of gases. But as the chain increases, because the molecules start to interact more and attract more strongly one another, then after pentane, as you can see, they are in liquid phase at room temperature. Up to 16 carbons, they are liquids. And then from carbon 17 and beyond, they become like solids, like waxy solid. They look like wax. They're not like a very tough solid, but nevertheless, they are solid, because the longer the chain, the more the molecules interact with one another, and they get stuck to one another, and that is why the state is affected, and it changes with the longer number of carbons. Now, a very, very important aspect of the alkanes, and remember, alkanes are all single bonds. So up to all our discussion up to now was on alkanes, which have all single bonds of this type, right? And for simplicity, let us think of long chains rather than branched chains. So all single bonds. Now, because they are single bonds, it's very hard to break them, because the truth is that we haven't spoken about energy is required to break different bonds, but I can tell you that the bonds between carbon-carbon and also the bonds between carbon-hydrogens, which we find in these alkanes, they require quite a lot of energy to break them. They are strong bonds. They are not weak bonds. They are quite strong bonds. So they don't break easily. So which means these molecules are whatever molecules, any molecule of alkane, it's actually quite a strong, well-bonded molecule. It's not easy to break. So for that reason, they do not react easily. They are unreactive, actually. They are unreactive substances. So all the alkanes are very unreactive. And in fact, in the past, they used to be called all paraffins. Alkanes used to be called paraffins instead of alkanes. Although paraffins, we still use this name paraffin for the fuel that we use sometimes to cook food, that we can buy. But nevertheless, in the past, all of them were called paraffins. And paraffin, the name paraffin actually means little affinity or something like that, which means unreactive. They do not react. And in fact, if you have paraffin or methane or whatever other alkane open in the air, it will not react. And you might find it very strange because actually the alkanes are very important fuels of ours, which you might think that because they are fuels, they are very reactive, but they are not. They are very unreactive. And yet, how then do we use them as fuels? How is it possible? It's because they need some help to react. So, for example, look at this gas that we use very often in the kitchen. This is a mixture of methane, and also it has a little bit of ethane, but mostly methane, the methane gas. I mean, if we have gas at home, it's actually this type of gas. And we know that we burn it. But remember, to burn it, we need to help it with a lit match first or something. We need to help it, to give it some activation energy at the beginning. And once it starts burning, then with the energy that, because this is a highly exothermic reaction, obviously we see fire. It's highly exothermic reaction. Then with the temperature that it generates by its burning, by the initial help that we provide, then it keeps on burning. But if we just keep the gas like that in the air on its own, it will not burn. We need to help it a bit. And then once we start the reaction with a little help, then it starts burning, and they emit a lot of energy. It's very hot, of course. That is why we call them fuels, and we use them as fuels. But they need this little help. So the very important reaction of the alkanes is their combustion, their burning. In other words, we can call it burning because we're talking about flames, fire. When there is flame and fire, we just call it burning. Now, how can we write this reaction? You see, when alkanes burn, in fact, when any organic compound burns, the products are always the same. They're carbon dioxide and water. These are the products of the combustion of any alkane, of any alkene, of any organic compound. So these two are always the products, and the only difference between the burning of different compounds is how to balance the equation. So for example, the first one here, we have the methane, which is just one carbon. If you remember, it's a gas. Methane burning means that they react with oxygen in the air. Always the burning is the compound plus oxygen, okay, always. And the products are always carbon dioxide and water. So here we have methane plus oxygen gives carbon dioxide and water, and of course energy, because these are all very exothermic reactions, we said. Now the difference between the burning of these different compounds that you can see here is the methane, here is the propane, here is hexane, octane, all of them with oxygen, as you can see. All of them produce carbon dioxide and water. Water, well, it would be produced as vapor because of the high heating that will be generated from the energy emitted. But even if we say liquid here, we wouldn't be wrong. Anyway, so it doesn't matter now what the states are, as long as we know that each of these compounds reacting with oxygen will give carbon dioxide and water. But it must be said, some of them are quite difficult to balance the equations. Maybe we should write one separately. Let's say, which one looks difficult here? Okay, the top one seems kind of easy, like the methane. Let's try the propane with three what are these, carbons and 8 hydrogens plus oxygen which will give us carbon dioxide. We're talking about the complete combustions of these alkanes. If there is enough oxygen, in other words, if they're burning enough oxygen, they will combust it completely and to produce carbon dioxide. If the oxygen is not enough, they will produce carbon monoxide instead. But for the time being, just learn about the carbon dioxide. Don't worry about the incomplete combustion. We only worry about the complete combustion. All right, now let us see, let us start from the carbons. Here we have 3 carbons. It appears only here, so it's good to start with carbon. And here in the carbon dioxide, it's only 1, so let us place a 3 here. Now, 3 carbons. Now, of course, this will affect the oxygens, but nevertheless, let's go to the hydrogens, because hydrogens also appear in 1 compound here and in 1 compound there. So here we have 8 hydrogens. Where do we find hydrogens? In the water, but only 2. So if we place it 4 here, 2 times 4 makes 8. So we balance the hydrogens as well. Now let us see the oxygens, because this is the hardest part usually. So we have now oxygens. 2 times 3, 6 oxygens here. This is not 6 here, this is oxygen. 6 oxygens. And here we have another 4. So it's 10 oxygens altogether. So here we can place a 5 and we balance it. All right. Sometimes we are going to see that here to balance the oxygen, we might have to have a ratio of a 2 of something. Not here. Here we don't need it. But some other times we do need it. And this can make it a bit tricky. I'm trying to find one. I don't know which other looks weird. Look at this, how many. Whew. Let's try and balance something different, which is not there, like the ethane. 2 plus 2, 4 plus 2, 6. So let's see. Can we balance this thing? This combustion of the ethane. Okay, so we have 2 carbons here. Let's place a 2 there. Hydrogen 6, and here 2. Let's place 3. Now the oxygens. 2 times 2 is 4, and another 3 from altogether is 7. You see now 7. What kind of number is this? It's an odd number. What do we do now here? We have a 7, and here we have 2 oxygens. What we can place here is we can place a 7 divided by 2, isn't it? Because now we have 7 oxygens. But now usually, we do not want our reaction to be balanced with ratios. We need whole numbers. So what do we do in this case? We just double all the other numbers. So instead of 1 here, we place a 2, and here we double it, and so that we'll get rid of this ratio, and this will this double will become 4, and the waters instead of 3 will double to become 6. So now our equation is balanced with whole integers as we want. So be careful. This is the difficulty I was talking about, that sometimes these reactions can be quite hard. Anyway, I don't think they will give you some reaction like this one, for, if necessary, I mean in an exam, but they might give us from the compounds which are lighter, like propane or ethane, the easier ones to balance, okay? So yeah, this is the only difficulty here in the balancing of this combustion of alkanes, or of any other organic compounds, that is, not just alkanes. So, but remember, the important aspect of the alkanes is that they can be combusted. Although we consider them to be very unreactive, they do burn, and they make very good fuels because they emit so much energy. Why do they emit so much energy? Because the bonds between carbon-carbon and carbon-hydrogen are quite strong bonds. So if they break, they release a lot of energy. of course, there's another type of reaction, but it's further away in your book here. We're going to see it maybe next week. Now let us talk about the alkenes. Just I'm trying to follow the flow in the book here, in your textbook. Now the alkenes have a double bond, at least one double bond between two carbon atoms, and therefore they have less hydrogens because of this double bond. And the general formula is this one. If we have n carbons, the hydrogens will be 2n. And this is provided that we have just one double bond between two carbons. So the simplest molecule of an alkene is, this is the simplest molecule with two carbons, which is Ething, because you cannot, with one carbon, we cannot have a double bond because just one carbon, okay? So this is the simplest molecule of an alkene. And we can symbolize it like that to match the alkanes, if just to compare them. But it's best if we draw the molecule this way, this displayed formula that is of their molecule, for future reference when we need them in future reactions. It will be easier for us to understand what's going on if we draw the molecule like that, like a bit crooked. Right. So, for example, I mean, could I draw this molecule instead of drawing it in this configuration? I could draw these two carbons of a double bond like that, and then the other bonds I could show them like that, a bit crooked, making this angle here. And this, particularly in this side, how could I show these complications here? You see this carbon, which is involved in a double bond, it is linked to one, two, what? They have done a mistake here. Oh my God. They have done a mistake. Oh dear, dear. Look at this. Remember, each carbon can form 4 bonds altogether. Sometimes 2 of these will be the double bond. So here we cannot, this is wrong. Look at this. 1, 2, 3, 4, 5. They have 5 bonds connected to this carbon. Oh my God. Look at this. This is nonsense. You cannot trust anything, and no picture from the internet. You have to check it, double check. Yeah, look at this. And of course, this one. These are mistakes. Somebody was drawing very fast. Yeah, so this, consider them missing. These are not there, okay? So each carbon here is connected to one hydrogen and one of this methyl group. One, 2, 3. Here, they should have the other hydrogen, not there. You see, there's another mistake there. Jesus, sorry. So one of these bonds now is a hydrogen, and this group here, it's a methyl group. It's this type of group. Okay, so we could show this molecule in this configuration, to follow this configuration here. So in other words, the difference between this molecule and this molecule is that this part, instead of hydrogen, is a methyl group, like here, methyl group. So it will help us a lot in the future if we draw these alkene molecules with this configuration, showing the whatever is connected to the carbons that participate in the double bond, like that, in this fashion. You're going to see it, and it will also help us to identify isomers of these alkenes, and alkenes can have some important isomers. Yeah. Look at this, but how can they have it so wrong? And I didn't notice it, just saw, oh, nice chains. Anyway, at least these ones at the bottom, which are different pictures, that these look correct. You see, this is the methyl group, and this is, actually, these are this is the same molecule. You see, it's 1, 2, 3, 4 carbons. No, it's not the same molecule. This is 3 carbons. Sorry, this is a propene, a type of propene, and this is 1, 2, 3, 4 butene molecule. Yeah. So this propene molecule here, we could draw it this way. The 2 hydrogens there, that is fine. And here would be the one hydrogen, this bond in other words, and the other bond would be with this methyl group again. All right. Yeah. Now the alkenes, okay, of course now our time has ended, but the alkenes, because of the double bond, are very reactive, well, very in comparison to the alkanes, and therefore there are quite a lot of reactions that we can discuss here. So anyway, we have to stop again and continue next week with the alkenes where we left. And guys, I hope you have a great weekend. Actually, we'll see you next week. Bye.